and for organizing the conference, which I'm really enjoying so far. And it's also convenient that I'm speaking after Eric, because he actually mentioned a lot of things that would be useful for my talk. First of all, just some practical information. The main references for what I'm saying this talk is this archive preprint. And if you would rather follow the slides on your own computer, they're available both on my website and on Tom's website. And as you can tell from the title, the topic of this talk is essentially rewriting. Well, Eric has mentioned rewriting briefly this morning, but for those who are not acquainted with the topic, my kind of brief slogan about what rewriting theory is that it's algebra with oriented equations. So in an elementary sense, algebra is about, well, we have some data and we have some equations, and then we can try to match one side of an equation inside in the context of some of the data that we're working with, and then we replace this kind of matched side of the equation with the other side of the equation. In rewriting theory, all we do is essentially give a preferred direction to the equations so that we can, for example, replace the left-hand side with the right-hand side, but not the other way around. And then kind of studying the properties of kind of the oriented algebras that are obtained with this kind of presentations. And the reason why it makes sense to talk about this in a conference on geometric and topological methods is that something that has come out of not even that recently is the idea of high-dimensional rewriting, which is a kind of unifying framework for various forms of rewriting various kinds of data, where, like, at least my view of the subject is that its central idea is that a rewrite system, such as the ones that I've been talking about right now, can be interpreted as a kind of cell complex, which is directed in a certain sense. So we have this kind of duality of something like rewriting, which ostensibly belongs to computation and algebra, and something like cell complexes, which essentially belongs to topology. So okay. Just to remind us what a cell complex is, informally, a cell complex is a space that is assembled from certain building blocks, which we can interpret as topological balls of different dimensions. And these building blocks are allowed to be glued by their boundaries, which can be seen as topological spheres, one dimension down. And on these balls, on these building blocks, there's a kind of recursive relation between balls of different dimensions, which we can see when we give a ball its a minimal regular cell structure, which has on the end ball we have a single top dimensional cell, and then for all k smaller than, for all dimensions smaller than the top dimension, we have two k dimensional cells, and this is an example for the two-dimensional balls of the disk, where you have this kind of dominant region, it's a single two-dimensional cell, and we have two one-dimensional cells, two zero-dimensional cells. So if I try to explain formally what a directed cell complex is, well, first of all, we just put directed in front of everything. And secondly, the idea is that as the idea that one should have in mind is that when we look at this kind of cell structure on n balls, we give the cells an orientation, and we give an orientation in every dimension. So this is it's slightly different from directed spaces presented we've seen in Uli's talk, for example, where kind of only one-dimensional paths are directed. Here the idea is that we consider this kind of relation, and we see one of the two k-dimensional cells in every dimension as kind of being the input or source side of a high-dimensional cell, and the other one is being the target or output side. So this is the idea that the directed n ball is it's an n ball with its boundary subdivided into one hemisphere, which you see as the input half, and another half which you see as the output half, each of which is in turn a directed n-1 ball. So this is a kind of particular kind of orientation on a combinatorial cell complex, which is actually inspired and comes from ideas of high category theory, because the way that these orientations have to fit together is what gives you a kind of a diagram which can be composed in a higher category. So when I say that rewrite systems can be seen as directed cell complexes, I'm going to give you just some intuition of why that is. So on a kind of basic level, we have this idea of an abstract rewrite system where the kind of the data that we are rewriting doesn't have any kind of inner structure. So like the things that we are rewriting can be just seen as elements of a set, which topologically you can just see as points. And then giving a rewrite system on a set is essentially giving a directed graph whose vertices are the elements of that set. And well, you can make the leap from graphs to one-dimensional CW complexes, and then a directed graph can be viewed as a directed one-dimensional cell complex. And then what we do in rewriting theory is consider kind of paths in this graph as being kind of a rewrite sequence, which tells us, this structure this is telling us that we can, starting from x, we can rewrite x to y, and then we can rewrite y to z, and so on. And the rewrite sequence traces kind of a path in the graph. And of course, paths are like they're homotopies in spaces. So a rewrite sequence is a kind of directed homotopy that follows the orientation of our edges. But now another just click there. Is there anything I can do when this happens?
Just click on the background of the screen.
Okay, great. So another really very rich branch of rewriting theory is the theory of string rewrite systems, where we rewrite kind of words made of characters in a certain alphabet, and now there is a kind of non-trivial structure to the thing, so we can match, a subword or something and apply the rewrite word. But so now the kind of the leap that we did to topology is that words can be seen as paths in a graph which has a single vertex and then one edge for every character of our alphabet. And so rewriting words or subwords can be seen as rewriting paths in this graph. And then a kind of a rewrite now can be seen as a two-dimensional cell going from a path, from one path to another path. And in this example is some kind of is a rewrite which we may see in something like presentation of a group. So this could be a group on, with two generators, A and B, and we can now we consider the word A inverse of A B as being a kind of path like this in a graph, and then we can rewrite A followed by A minus 1 to the unit of a group, and then we can rewrite 1 followed the unit followed by B to B. And this kind of thing traces a kind of directed homotopy in a two-dimensional directed subcomplex. And just very briefly, another huge branch is this term rewriting systems. And there is a way that's kind of come out, I would say, from categorical universal algebra, and the idea of flow-beard theories, for those who know this, where you can faithfully embed a term rewriting system as being a rewrite system inside a Cartesian monoidal category. And through this kind of embedding, a term rewriting becomes diagram rewriting in some particular monoidal categories. And monoidal categories are a special case of two-dimensional categories. And so kind of what happens is that you end up with embedding term rewriting as a kind of rewriting of two-dimensional diagrams. So, for example, something that could show up in a presentation of again of the theory of groups or monoids, we have a multiplication, which takes and we may have a kind of presentation of the associativity rules, which tells us that multiplying x and y and then multiplying z can be rewritten to a multiplication of x by the multiplication of y and z. And that kind of in this kind of categorical view of term rewrite systems becomes the rewrite of this kind of two-dimensional diagram to this two-dimensional diagram, which can be seen as a three-dimensional cell. Okay. So everything I've said so far has been very informal, and that's something that I wanted to do, because the point is that exactly as with cell complexes in topology or combinatorial topology, we can have several models, several data structures which embody the idea of what a cell complex is. And what we need in order to have such a data structure is that we need some model of what the n cells or what the n balls are, and what their boundaries are and how their boundaries are included. And then we have to have a model of how we can glue the n cells together. Okay, that's kind of the basic data that we need to give a model of a cell complex, and it's the same for the directed cell complex. And there can be a variety of flavors of models. Of course, in topology, we have point set models where the balls are actually topological, closed topological balls, and the gluing maps are continuous maps of these things to topological spaces. Because we have combinatorial models, simplicial complexes or simplicial sets are combinatorial models of the same thing for cubical sets. We can have algebraic models, and now I'm thinking more of the directed concepts in a minute. And as we've seen in Eric's talk, we can have also kind of models which have a syntactic or logical flavor. Because, for example, Eric was talking about higher inductive types, and those can be seen as a kind of syntactic way of specifying the cell complex inside inside a type theory. And this idea of rewrite systems as directed self complexes has emerged from this model of polygraphs. It's an idea of Albert Bourny, where a rewrite system is actually modeled by a freely generated strict n category. And what this translates to is that an n cell in this model is modeled by the free n category on something called the n globe. This is the these are the shapes that underlie globular sets. If you've seen that, so this is how you can represent the first few n globes. And once you can see these kind of n cell objects inside n categories, then you can use functors of strict I categories to glue them together. So this is an example of what I was calling an algebraic model, because of course strict n categories are models of an algebraic theory, actually an algebraic theory over globular sets rather than sets. So all these things are kind of specified by an equational theory on terms. So there's a kind of algebraic description of how we can glue cells together and what the outcome is. So when we try to build a model for high-dimensional rewriting theory, I would like to focus on kind of on three problems that we face, or rather, or three questions that we need to consider whether something is a good model, which I call expressiveness, topological soundness, and high categorical semantics. Expressiveness is just the fact that, well, the starting point of high-dimensional rewriting theory is that it kind of unifies all these flavors of rewriting theory that people are actually interested in. Like, well, it's the examples that I've given. So there's a way of putting abstract rewrite systems in this. There's a way of embedding string rewrite systems, and there's a way of embedding term rewrite systems inside. And that's something if you want that should be kind of starting point. If you're going to to sell this product, this idea, or should really be doing directed cell complexes, you want to be able to tell rewrite theory practitioners that you don't have to throw away what you've been doing so far, unless there's a very good reason. A different problem is the idea of topological soundness. It is that the directed cell complex should also be a presentation of a topological cell complex. So, and as the word suggests, that when you have a directed cell complex, it should be a cell complex together with some additional data. Actually, a cell complex together with a specified orientation. And you want to have a kind of a good way of forgetting this orientation and transforming what you're doing into a kind of a proper, undirected topological cell complex. And according to the interpretation, also you want a well-formed rewrite sequence to induce a cellular homotopy in the presented space. And why is this useful? Well, first of all, it means that kind of rewriting proofs that you can do in the theory can be actually used to formalize homotopical algebra, and also it means that everything that you're doing in the system also has it can be used to do properly combinatorial topology. And finally, another problem is that, as suggested by this idea of, for example, embedding term writing systems such as presentations of algebraic theories in this context, is that usually rewrite systems also want to be interpreted in a certain way. Like presentation of an algebraic theory wants to have interpretations as models of that algebraic theory. And something which is clear to category theorists is that, well, categories and high categories tend to be natural contexts for interpretation of algebraic theories and high-dimensional algebraic theories. And so it is once you have a model of high-dimensional rewrite systems, you want to have an associated model of high categories that can function as universes of models for whatever is presented by the rewrite system. And so again, just one point that I want to make is that there is the relation between high-dimensional rewrite system and high categories is a syntax semantics relation. So it is that the rewrite system is a syntactic object which can be interpreted in a high category, but it does not necessarily have to be a high category. So looking at this kind of original setting for high-dimensional rewriting, we can ask, how do polygraphs do with respect to these problems? In terms of expressiveness, I would say they do great. It's an extremely expressive, and that's kind of one of the motivations that really you can. There's no kind of necessity of doing much encoding from traditional forms of rewriting theory into polygraph theory. Somehow things just can be naturally embedded and interpreted. But the kind of the sticking point is mainly the issue of topological soundness, and there is a kind of precise sense in which there is no way of soundly interpreting polygraphs, like general polygraphs, as undirected subcontext. There's no functor from the category of polygraphs to the category of topological spaces, which does what we want, that is, turns a kind of directed subcomplex with certain generators to a corresponding subcomplex with the same undirected generators. And that is due to this problem with strict Ekman-Hilton, where Eric mentioned Ekman-Hilton and the fact that you have this braiding in pi 3 of S2, and in polygraphs, as in strict two categories, this kind of braiding becomes degenerate, and it becomes kind of a trivial homotopy. And in terms of the primal categorical semantics, you do have a kind of quite rich universe of semantics. The polygraphs live in the same context as strict high categories, but it is limited to strict high categories, which do not cover all the kind of, and especially when you look at the strict high groupoids, they do not model all possible spaces or all possible homotopy types. So we have a kind of quite rich context, quite rich context, but not all the context that we want. And I'd like to just point that there is a kind of duality between, or a kind of bargaining to do between number one and number two, because this problem of topological sumness fails because polygraphs are somewhat too expressive, in the sense that these gluing maps of polygraphs, there's too many gluing maps, so that not all the gluing maps can be interpreted as topological gluing maps. So number 2 fails because the kind of strict and omega categories that are used as foundation for polygraphs are not kind of expressive enough. There's too few. So there's too many syntactic objects, too few semantic objects. So an alternative is try to, let's start by thinking of some model of high categories which fixes number 2. And something that we could look at is all these models of high categories based on various cell shapes. There's globes, symphyses, cubes, homotopes. When you do that, well, we kind of basically just by the approach we're taking, we fix the problem with number 2. We start from something which has a kind of established model of really high categories and so on. Usually, because we kind of if we use quite simple shapes of what the cells can be, we also usually have a geometric realization. Of course, we have symphyses and symphyses, cubes, and globes. I'm not 100% sure what the situation is for general opticals, but it should also be doable. However, we have a big problem with expressiveness because if you think about, for example, the case of string rewrite systems, right? So a 2-dimensional cell with kind of n input 1-dimensional cells and m output 1-dimensional cells corresponds to a rewrite of a kind of string of length n into a string of length m. And of course, string rewrite systems tend to want to have freedom as to how long the input word is and how long the output word is. For example, if we use globes, the only 2-dimensional cell shape has a single 1-dimensional cell in the input and a single one in the output. So we can only rewrite single characters. With symphyses, we can, well, depending on how we orient them, there's the typical kind of street orientation of symphyses has 1 input thing, 2 output things. So we can only rewrite 1 character into 2 characters. With cubes, we can only write 2 characters into 2 characters, and so on. Homotopics do a bit better because we can rewrite 1 to many or many to 1, and that already covers quite a lot of interesting stuff. Context-free grammars can be done homotopically, but there's still a lot of kind of traditional rewriting here which is not covered by these shapes. So what I'm trying to suggest is, there is this trade-off where we can have topologically sound models of directed cell complexes, which are not kind of expressive enough. But then if we go too far into expressiveness and we consider polygraphs, then we end up being topologically unsound. And so the approach that I've been trying to take is to see what happens if how far can we push kind of expressiveness by staying this side of this soundness divide. So the goal is to have a large and expressive class of directables and maps of directables while keeping topological soundness. So it's if you look at it from this viewpoint of shape categories, it's to have kind of a large shape category with good properties, with good rewriting properties, but that still has a good geometric realization. So the starting point of is this very classical result of combinatorial topology. So regular CW complex is a cell complex in which the inclusion of every cell is homomorphism of its image, meaning that when you attach a ball, it still remains a ball in the target space. So that is a result that a regular CW complex, a basic operation we can do is pass from CW complex to phase poset, where you only remember the information of what cells are in the boundary of cells. And when you have a regular CW complex, then you can recover the original CW complex up to cellular homomorphism from its phase posets. So you could say that phase posets of regular CW balls are combinatorial models of balls. So the idea now is to take this as like a combinatorial encoding of a directed ball. So take a phase poset, but now enrich it with some orientation information by again taking the phase poset and then remembering additionally whether a cell is the source input half of the boundary or whether it is in the output or target boundary. And so this this results in this kind of data structure. So well, this is a standard definition of finite poset is graded if for every element of the poset, and we consider all the maximal descending chains under X, then those chains must have the same length, which kind of gives a kind of intrinsic rank or dimension to the element. And if these chains have length k, then we say that the rank or the dimension in this case, I'm going to say dimension, though that's slightly non-standard because I want this idea of this being cells. Then dimension of X is k plus 1. Okay? Basically, all paths, all downward paths from an element in the Hasse diagram of the poset have the same length. And then an oriented graded poset is a finite graded poset together with an edge labeling of its Hasse diagram with 2 colors. So we label the covering relation of the poset by saying, okay, this is covered as an input phase or this is covered as an output phase. Then kind of sub shapes of this kind of description correspond to downwards closed subsets of a poset, and well, downwards closed subsets of a graded poset are still graded, and we can give them an orientation just by restriction. So downwards closed subsets also inherit the structure of an oriented graded poset. And the good thing is that in an oriented graded poset, we have a combinatorial definition of boundaries of closed subsets, which works this way. So for any, so we want to say what the, given a closed subset, we want to say what the input k-dimensional boundary and the output k-dimensional boundary of that closed subset is. The way we do it is we consider first this set delta alpha kq, which is the set of all the k-dimensional elements, which whenever they're covered, whenever they're the face of an element of U, then they have this orientation alpha. So for example, they're the k-dimensional things which are always input faces or always output faces whenever they're a face of some element of U. And then we can also consider the maximal elements of any dimension in the poset, in the closed subset. Maximal in the sense maximal in the subset, so not covered by any element of the subset. And then our definition of the k-dimensional input or alpha boundary is given by the closure of the downwards closure of this set together the union of the closures of all these maximal things. So we put all these things, we put everything which is below these things in the set, but we also put everything which is not actually below any element of dimension k or larger than k. And just some notation that, well, I'll just write boundary of x for boundary of the closure of an element x. And then we can use these boundary things to define what a morphism between oriented graded posits is. And we define a map of oriented graded posits as a function that preserves all these boundaries for all elements. So the image of the k alpha boundary of x is the k alpha boundary of the image of x for all elements, for all k and for all alpha. And what we get is that a map defined this way is always order preserving. It's always dimension non-increasing, and it is also closed, max closed subsets, closed subsets. And an injective map is in fact dimension preserving and is a poset embedding. It's important because it tells us that the map of oriented graded posets has an underlying order preserving map of posets. So then in this way, we kind of defined a category of these kind of combinatorial structures. And now we want to kind of individuate a subclass of these structures which actually correspond to models of directed and balls. And we do that by specifying it's inductively the things is this defined class which we call regular molecules. The terminology comes from some works of Richard Steiner, who did some related things in the 90s. And just a warning, like regular molecules, they're not all of them are what I would consider directed and ball, but they could just be kind of sub complexes of directed and balls. I'll tell you later what is a directed and ball. So these are the three clauses. First of all, we say that the terminal oriented graded poset, which is just the one element poset with no orientation data, is going to be a regular molecule. Then I was telling you about this kind of recursive relation between balls, and that's kind of given by this atom thing. This is telling us that we have two regular molecules of the same dimension, and such that their codimension 1 boundaries, both input and output, are isomorphic. And in addition, they have to be round. I'm going to define what round means later, but basically roundness is the missing piece of two regular molecules to give you actually a directed and ball. Then we can form this n+1 dimensional regular molecule, which is essentially taking U as the southern hemisphere, V as the northern hemisphere, and then putting one cell going from the southern to the northern hemisphere. And that's going to be still part of our class. And then finally, we have this kind of pasting rule, which has that if U and V are regular molecules and the output k-dimensional boundary of U is isomorphic to the input k-dimensional boundary of V, then we can kind of glue them along this boundary. So it's a kind of way of gluing together these things that respects direction in a certain sense. So you can only glue an output thing to an input thing. So there's a few more details about this. So yeah, this idea of gluing is realized as a push out in the category for integrated posets, and then to just push out along this isomorphism. With their boundaries, we add a kind of greatest element to the poset with orientation saying that everything coming from U is input, everything coming from V is output. And so I've just been saying R isomorphic. In principle, you could think, oh, there could be many isomorphisms giving different results. But in fact, it's a result about this class of regular molecules that when they are isomorphic in a unique way. So there's uniqueness, like there's a unique also way that you can glue them together. So this is an example. If you have U, which is kind of path of two edges, would be a path of one edge, then this would be the result of this rule. Then I'll mention this roundness property, something that you can also prove about these regular molecules, that they satisfy this relation, that the k-1 boundary, this means this is the union of the outputs, it's the entire k-1 dimensional boundary, is always included in the intersection of the input k-dimensional boundary and the output k-dimensional boundary. This is not always, this is always an inclusion, it's not always an equality. And we say that U is round if all of these, for every k smaller than the dimension of U, all of these are equalities. So this roundness ends up capturing exactly the idea that these things are going to be homomorphic to balls. So for example, these are examples of things which are regular molecules, but they're not round. For example, here in this one, the input one boundary is this, the output one boundary is this, and the zero boundary is given just by this point, and you can see that the intersection of these two also contains this point in the middle. On the other hand, these two kind of directed cell structures are round, and indeed you can see that they are topological disks once you forget orientation. So pasting, like this paste rule, that's what I've been telling you, and again, it's expressed as a push out in this category for integrated process.
So in the new
Yes.
so it seems that the one with the right is right. So
Which one?
So the intersection contains 3 points, right?
Yeah, the intersection contains 3 points, but the zero dimensional boundary is only 2 points.
But so then the inclusion is satisfied.
No, I'm saying roundness means that the opposite inclusion is satisfied too. Yeah, it's they need to all of these inclusions must be equalities. So an example of pasting is that well, we can consider this example which I've been saying. And the thing about the paste rule is that there is not a unique way of naming something to paste. So, for example, this kind of regular molecule can be obtained either as first building this thing and then gluing this thing along the one-dimensional boundary, or it can be obtained by taking this one and gluing it along the one-dimensional boundary with this one. But it can also be obtained by taking these two directed globes and gluing them along the zero-dimensional boundary. Okay. So as I promised in this model, the idea is that round regular molecules, so the integrated processes that are obtained, that are round and obtained inductively by these rules are a combinatorial model of what a directed ball is. So something that I hope to have time to show later is that something I'll be working together with student Diana Kessler is implementing these data structures, and also what I'm going to show later, computational implementation is in a Python library meant for how to measure writing or directed combinatorial topology if you want. I'm going to try to give a quick demonstration of this at the end of the talk. This is still not publicly released, but we are hoping to release it in the next couple of months. So, okay, so now we are able to define this kind of category of shapes of directed laws, and we're going to take the as objects, so as building blocks, we're going to take the regular atoms, which are the molecules which have either the molecules which have a greatest element, or the molecules that are obtained by the atom rule. Anyway, that just do the same thing. As morphisms, we take all the maps of these things as oriented-graded foci. And morphisms, like many other of these kind of shape categories, morphism factor as surjections followed by injections. So this is what's called a reedy category sometimes. And then kind of our model of what a directed cell complex is going to belong to the category of pre-sheets over this shape category. The idea is that it's a kind of space modeled on these shapes. Okay? The atoms are always round. This is a very rich category of shape because it contains lots of subcategories as full subcategories. In fact, the category of simplices is contained in here. The category of reflexive globes, so one of the ones where you also have kind of units morphisms contained. This category of cubes with connections is contained, and also this category of positive objects with contractions. I'm not going to define what these are, so this slide is only for those who are already in the know. And furthermore, what's really useful is that this category is also closed under a bunch of operations, ways of putting together shapes. So it's one operation is this kind of reversing the direction of cells in a given dimensions. So it is closed on after this, so you can reverse all the orientation in any given dimension, and that's still going to give you something. It is closed under suspensions, which it shares only with the category of globes. It is closed under gray products, which are disoriented version of Cartesian products, which is shared only with the category of cubes. And it is also closed under entered version of the topological join operation, which shares only with the category of simplices. So somehow all these kind of closure properties that are kind of where you have to kind of pick one and with kind of simpler shape categories. In this case, you just take them all. So, well, not only atoms, but also regular molecules in their maps can be embedded as kind of special cases of maps. So diagrammatic sets is just some terminology. So if you use a regular molecule and X is a diagrammatic set, so it's a pre-sheet over these things. I call the morphism from the embedding view to X a diagram of shape U. I called it spherical boundary is what I used to use for round. Then I realized that round is snappier. But if U is round, then I call this composable diagram. And if you use an atom, I call this cell. So okay, so this is a brief description of this model. And now, how does it do with respect to these three questions I had? In terms of expressiveness, I can't make this very precise, but my feeling is that this is very similar to polygraphs. The main restriction is this roundness or Feldberg boundary constraints on cell shape, which is absent in polygraphs, so which kind of forbids you from having cells with strictly degenerate, strictly low-dimensional boundaries. However, you have this system of surjective maps of these kind of degeneracy collapses, or whatever you want to call them, inside the shape category, and that give you access to some kind of way of getting weak units and weak unit force inside this theory, and these can be kind of used to kind of head diagrams in a way that then allows you to rewrite them. So, for example, in the theory of polygraphs, it's perfectly fine to have a rewrite which takes this kind of diagram and turns it into this one, as long as this kind of point y is equal to this point y. And we can't do this in this context. However, there is a degeneracy map from the shape of this diagram to the shape of this diagram, which collapses just one edge, one arrow, and then by pulling back this diagram along this degeneracy, we can get this kind of, we can get another diagram, and now on this one we can rewrite this one into this one. There are also more systematic ways of adding kind of non-round diagrams to make them round, but the point is that, I mean, probably in practice it would be more of an art than like be more about choosing what the smallest, most useful paddings are. So next, this topological soundness. It's a yes, because we have this chain of functors where we can take this atom category. As I was saying, we can forget direction, and then we get posets and maps of posets. Then we can take the nerve of a poset or the order complex, it doesn't really matter. We get a simplicial set, and then we can take just the usual realization of simplicial sets. And that can be, for kind of usual categorical algebra, this can be extended to presheaves and gives you an adjunction between diagrammatic sets and spaces and this functor is going to be what we consider to be a geometric realization. And we can prove that if you use an n-dimensional atom, its realization is homomorphic to the n ball, and the realization of the boundary is homomorphic to the n-1 sphere. And it's kind of almost an immediate consequence that if X is a kind of cell complex so something which is built like a cell complex in this category of diagrammatic sets, then its realization is a CW complex with the realization of the generating cells as generating cells. So this answers positively to the problem of topological soundness. And finally, I'll be very brief about this in terms of categorical semantics. We do have a kind of a model of weak high categories that lives on top of this model of rewrite systems. The idea is that a high category is this complex is a diagrammatic set in which every composable diagram is equivalent to a single cell. So you can always, the idea is you can always rewrite a kind of a round diagram made of several cells. You can always rewrite it into a single cell that we consider a sweet composite. The equivalent here is with respect to precise definition of what an equivalence diagram is. So these are kind of pictures you have in mind. These are kind of diagram, and you can find there exists always a particular kind of equivalence diagram which turns this into a composite, and this can be also inverted going the other way. And again, I still haven't worked on comparing this model with other more established models, but I mean, I conjecture that this is a good model of kind of high categories in the fully weak infinity sense. Just briefly about further work. Kind of the one other paper in this, which you can find now, is an application of this to kind of presentations of higher right theories. So the idea is that this whole setup now can be used to kind of import topological ideas into rewriting theory. And this one takes a look at a kind of oriented version of this mesh product of pointed spaces and shows that it gives something. It recovers a construction of kind of higher algebra with some additional interesting, like, homotopical data in it. And I'm going to end with, well, my question for participants here, because again, I've been interested in this from this rewriting perspective, but of course people here look at directed spaces or non-directed spaces for all sorts of different reasons. So I'd be interested in seeing whether this model can help in any way, can be applied to questions of directed topology and concurrency, for example, whether is there a use for high directed cells in this context? Are there combinatorial versions of some of these invariants that people have been computing that can be computed for diagrammatic sets? The other question is, well, one thing that I've had by kind of using these kind of structures and also working on their implementation is that this kind of direction data actually is helpful even if eventually you want to do undirected things, because basically it gives, as I've tried to demonstrate, how it gives an algebraic grip on gluing together things. Like instead, in general, like if you don't have direction to give a gluing, you have to give a kind of a, you know, a particular span of maps, for example. But somehow having this orientation gives you this kind of system of coordinates in a way. You can just say, oh, I want the k-dimensional upper boundary, and that, you know, it's a kind of algebraic way of getting sub cells in a way and putting them together. So yeah, I mean, I'm not saying anything. I'm just trying to see whether this is something that can be used, because that's, I think that can be very useful for, you know, computing formally with these things once you can specify things algebraically rather than combinatorially. So thank you. I think I'm kind of out of time. I was hoping to show 5 minutes of the software implementation. Am I allowed to?
I guess.
When you ask a question, asking
Or maybe I can take questions and then maybe
Yeah,
maybe I can.
I have a question. When I was listening about these rewriting systems, the first sound that came to my mind was the discrete-mode theory. You know, when you have this system, I know it's the same when you can interpret this idea of low-path definition of the cells into another path. And
You know, sorry, which
because you have, suppose you have the regular complex.
Yes.
That's the big complex, and then every time you have these non-pairs, non-equivalent cells and the C-sig match.
Yes.
Have this low-path sort of rewriting of the homotopy mark. So homotopy is an analog or an interpreted.
So I mean, I suppose in some context, the kind of the orientation that you already have in these diagrams may give you something like these matchings and discrete modes theory, where it gives you a kind of specified way that you can collapse things towards, for example, their output. And I don't know how many of the kind of actual situations that you want to model this capture, but it's definitely crossed my mind, and I would like to explore that. I think in general, not like definitely not all the kind of matchings that you may want to consider in discrete Morse theory give you a kind of a composable diagram, for example, because that's these diagrams have a very special way that they can be composed, where kind of there's a flow from input to output. But yeah, I'm definitely very interested in understanding that.
Also related to what you were saying at the beginning, so Morse matching are very restricted form of writing. You would want to write one cell whereas your ID you want to consider maybe more general situation.
So yeah, I'm just going to show you a couple of things in this. So so first of all, yeah, there's in this library. So this kind of idea of regular molecules and shapes is implemented as this data class shape. So this has the kind of constructors that I've been talking about. So for example, you can I'm okay if I'm stand. Actually, thank you. So if you remember, we had those kind of, well, the starting point was always the point. And then, for example, the way that you get an arrow is by using this kind of atom constructor between 2 points. And now you can see, for example, well, this allows you, you have some visualization. So this would be the arrow as it's as this kind of oriented pose set here. The pink arrows correspond to inputs, and the blue arrows correspond to outputs. It's true, the inputs are reversed, and the idea is that I'm kind of trying to capture this kind of flow from inputs towards outputs. And, it's another kind of way of encoding the structure. Instead of labeling, you remember the grade, and then you reverse some arrows. So let's do something slightly more complicated. So we can. Pink one is minus and blue one is plus. Yes. So we can do this kind of pasting operation. Again, I should write pasting along the zero boundary here, but actually, if you don't have anything, it kind of defaults to the minimum of the 2 dimensions -1. So it's fine here. And then I can form an atom with that. I'm going to call this binary. So it is going to be like a 2-cell going from. It's going to be a 2-dimensional ball with 2 things in the input and 1 thing in the output. Well, you can see this again as a Hasse diagram, but more useful is this visualization as a string diagram. Actually, so the idea of this representation is that this is a diagram in which the nodes correspond to top-dimensional cells, and the wires correspond to codimension 1 cells, and kind of going from bottom to top separates the faces in input and output faces. So this can be, so in this case, that's the node is the 2-cell, and the things at the bottom are the input 1 cells, and the thing on the top is the output 1 cell. And well, in fact, these constructors actually separate these shapes into various subclasses corresponding to it. So for example, in this case, it correctly recognizes that this is also an orbital. So not the, but actually, well, in addition to these kind of basic constructors, there's also some kind of more refined or more high-level ones. So for example, I told you that we have all these subclasses of shapes. So for example, we have a constructor which just gives you the simplex given dimension. So for example, I can I can do the three-dimensional simplex of the tetrahedron. And well, if I draw this as a string diagram, it just gives you this kind of separation of the boundary of tetrahedron into two input triangles and two output triangles. It's also useful to see this as being kind of, so this is the representation of the input boundary and the output boundary of the tetrahedron. So this can be seen as a rewrite from this to this, which in the kind of algebraic, in the kind of algebraic view of rewrite system, for example, this is the shape of a co-associativity equation, for example, in the theory of co-algebras. Okay, so this is kind of how this kind of handles shapes. I'm also going to quickly show you the actual complexes. So these are done by these are handled by they're implemented as this class Diag set. I'm going to call this GETCO. So this corresponds to, this has now created an empty cell complex. We can see all the things that we can do on it. So the main thing is that we can add generators. So for now, I can only add points. So I'm going to add a point, and I'm going to give it the name X. This is also going to return the diagram corresponding to this generator, and I'm going to assign it to the variable X. So now you can see, for example, in the GETCO itself, it tells that now it has a, well, you don't actually see what I'm writing. There's well, I guess I just have to press enter a few times. So then, for example, we can try to construct a kind of torus and there. So we have now we have a complex with a single cell, and now I'm going to add two kind of loops in this thing. I'm going to call them A and B. And then I'm going to add a two-dimensional cell P that goes from A followed by B to B followed by A. So again, I can draw this as a string diagram. You can see it as the rewrite of A, then B, B, then A. If you take a geometric realization of this, it's a torus. If you consider it algebraically, it's a presentation of the commutative monoid in two elements. So you get all these different views of what the objects are. I have some worked out examples for. So Eric also mentioned the kind of Beckman-Hilton argument, and so I can't remember what this diagrammatic set is called, but I'm going to just call it EH in big. Oh, sorry. Okay, so it's because it's so this EH, this is already a workbook. Because I have to do the AND. So EH now is a Diag set, and it's a Diag set with a single unnamed point and two two-dimensional generators. So it's like it's a kind of bouquet of two spheres. And now you have actually a proof. Is EH? It's alright. Well, it's a there's a EH well, you see it's a diagram object, its dimension is 3, and it gives you a proof. It's actually a formal proof that that you can kind of commute, that you can make A slide past B, so you can permute A and B in the you have a homotopy between A followed by B to B followed by A, and you can also you can also do this. Let me just try. I can't remember. Generate layering. You can kind of layer all the kind of generators that appear in this, or rather all the cells that appears in this diagram, and show it as a kind of sequence of rewrite steps. So you start from A below B, then while you create some units, you create this kind of train track in the middle. You move B to one side, A to the other side, then you make them slide like this. This is kind of automatically generated starting from this diagram. So anyway, this is just a few things that you can do with this, and yeah, and there's probably a lot that I haven't thought of. So I'm kind of happy to get suggestions and feature requests. And okay, sorry for going so past my time, but this is all I want to say.
So unless there is a very good question, I suppose that we stop here and go to lunch. I guess about
and talk on the